Hello everyone, and welcome to this video on tutorial 10 question 1. Assume that S follows a geometric Brownian motion. So we have this definition. Use Ito's formula to find processes for these different situations. In each case, express the coefficients of dt and dB in terms of y and not s. Okay, so let's get stuck into this. So firstly, Ito's formula. This will be given to you in the exam. It won't be in the formula book, but it will be stated in the question. It says that for f, a sufficiently smooth function that the following equation holds. It says that df, suppose this depends on t and s, is given as follows. So it's the derivative, partial derivative of f with respect to t dt, the partial derivative of f with respect to s of t ds of t, and there's this additional term which relates to the second derivative of f with respect to s, multiplied by ds of t all squared. Okay, so this is Ito's formula for a function depending on t and s, and f is assumed to be sufficiently smooth. I'm not going to go into those conditions. Let's just say it's smooth. This is given to us. We also know that the process S follows a geometric Brownian motion. This will not be given in an exam. You might be expected to explain it or define it or use it or prove various things that come from this particular model. So in this question, conveniently is stated for you. And we know this process follows ds dt, so infinitesimal change in the process S is given by mu st dt plus sigma st dB. Okay, so here mu and sigma are the mean and the volatility. Beta, this is a standard Brownian motion. Everything else stands for what you'd expect it to be. S of t is the share price. Okay, so this is the two pieces of information we're given. These two, and notice that these ds's are the same, so we could substitute the second one into the first one, and before we do that we should square ds, and there are some properties we need to recall. So these are the properties we should recall. dt times dt is 0, dB times dB is dt, and the cross terms, the dB and the dt, multiply equal to 0. So if we simplify, so I call this 1, maybe go to a different color. So if we simplify 1, so we want ds all squared, ds of t that is. So we want mu s of t dt plus sigma s of t dB all squared. Okay, I think I'm going to write it all out. Oops. So that's the square of the first term. That's the square of the second term. No, sorry, that's the cross terms, and now the square of the last term. There you go, and that's the square of the last term. Okay, so using the properties in blue, dt is 0, so that term's gone. dB dt is 0, that term's gone. So actually ds squared is simply the volatility squared, the share price squared, dB squared, which is actually just dt, which is this this middle property here. So actually we needed all of those properties in blue. Okay, so we've now simplified 1, so we can drop it in to the first equation and simplify. So let's do that next. So if we drop it into the first equation, let's get them both on the screen. Just do that. So df is equal to partial derivative. I think I'm going to go to, how am I going to do this? Let me think. Okay, yeah, so df dt, just wondering whether to write all the arguments because it's going to get quite long. I think I'm going to miss them. So I'm just going to write df dt, and I'm just going to assume that's a function of t and s. I'm going to take the dt out, so I'm going to open a bracket, and I'm going to have some dt's from the equation, from this term here. Okay, I think I can see it. So it's 1/2 sigma squared s squared dt, s squared d d2f d of what? I've lost it. Oh, ds squared, there it is. And that's all times dt. And now the ds term, that's just the middle term. Okay, I'll put in a bracket. I think I'll call that ds dt. Okay, so there's my first equation for f, which depends on t and some s of t, so I think I'll just call it just x for now. Okay, so this is going to be quite important for when we get stuck into the particular processes. So if we take a look at the three processes, so this is going to be useful for the third one because this depends on s and t. We now need to build equations for the other two, which only depend on s. So let's take a look at that next. Okay. So I really need to highlight this. This is my first really important equation. Let's go to the second one. So on the other hand, if f does not depend on t, so only depends on the share price, then Ito's lemma, this is the following. It becomes df, which depends on the share price only, is df ds plus 1/2 of d2f ds squared multiplied by ds all squared. Okay, so that is the second equation coming from Ito's lemma for the function only depending on only depending on s. So same as before, we need to simplify this, and we can recycle some old information. We can use this. We can drop this this equation we found into the latest equation. So let's do that next. So this is going to give us our second important equation. What we find is df, which depends just on s, and s depends on t, but we're not going to worry about that. Just think about it changing in terms of s. Okay, so we're going to collect all the dt's. So we have dt's coming from this second term, the half business. Oh, actually, we've got this here, this ds. We should substitute in, okay, if I just call that star, because we know it's a geometric Brownian motion, we can substitute in this one. And this has dt's and db's. So if I'm going to collect together all the dt's, I'm going to have one coming from here. So we have mu st multiplied by the df ds plus, coming from the reference 1, we have half sigma squared s squared d2f ds squared dt, and finally the db's, we have, let's see, so that's coming from the top, we have the sigma st df ds all multiplied by dB. Okay, so that's our second important equation. I've just noticed that here I could have done a bit more with the ds. I could have put in the Brownian motion. No big deal. Maybe that'll be something we need to look at later on in the question. Let's just see how it goes. We've got the important equations for now. So this is the second type, where the function only depends on the share price. Okay, so let's take a look at the first condition. Now we've derived those. The first process is actually, I'll call it a little s. df ds is equal to s to the n of t. So I'm going to consider this one because I want to know what happens with the process y equals s to the n. So we're going to use the second equation in yellow. Okay, so the partial differentiation next. If we differentiate f with respect to s, so I'm calculating this number here when it comes up. There we go. Df ds is n s n minus 1. I need the second derivative of f with respect to s, which is n minus 1 s n minus 1. And I've already got that one. So I've got all the partial derivatives. So I'm now going to drop them in. So using Ito's equation, we know that the d of Sn, so this is just d of y, is equal to mu st, drop in the partial derivative, plus half sigma squared ds, oh, we've got that, the second derivative, times dt, and then the second term we have sigma s of t n Sn minus 1 of t dB. Okay, so now I want to simplify this. I think there's a little bit we could do. I can see that the Sn minus 1s and the S's come together. So we have that in the first term. In the second term, have I missed something there? Is that right? Oh, I've missed the squared. Oh, okay, let's write it on in blue. I missed the squared there. Okay, so they come together to 1/2 sigma squared n minus 1 Sn of t dt, and the next term is sigma n s to the power n of t dbt, and we are done. We have shown how the process behaves. We have shown that dy, which is dsn of t, is mu n plus 1/2 sigma squared n minus 1. And the Sn is just y. So I can change the coefficient back. Plus sigma n y dbt. So there you go, that completes the answer. There's quite a bit to do there, it's quite fiddly as well. It involves a little bit of thought. I think once you've derived the first two equations up here in yellow, once you've got these, and these calculations are always the same, once you have those, I think it's not too bad. You just need to look at them and say, right, I need the partial derivatives. I think these standard calculations should be quite simple. Then drop them in and just collect them all together. So really this is algebra heavy more than anything. And there's 3 parts to this question. Once you've worked your way through them, you realize a lot of the process is routine, and it starts to become more natural once you've done a few more. Okay, so I think I'm going to split the video. Let's take a look at the next question. question in the next video.